This is a module on the economics of climate change, but I'm going to start by talking about the science of climate change. Now, obviously, this will not be examined, but I do this for two reasons. One, if you want to solve a problem, you need to understand the problem, right? It's always good to actually know what you're doing. So that is important. Now, most of you have picked up things about climate, the science of climate change. So you guys are in your early 20s, right? And this has been at the front pages of newspapers for the last 30 years. When I was your age, I needed to explain to people what is climate change because they did not know about this. But that is no longer the case, right? And the problem with what you have picked up from the media and so on and so forth, or maybe even in the classroom, is that people talk all sorts of nonsense about climate change. Really complete and utter bollocks you can find even at supposedly high quality. The light is shining in my eye, so I didn't see you. Sorry, go ahead.
What's your top 5 nonsensical things?
I was actually getting there. You can get all sorts of nonsense, right? Even in supposedly high quality outlets such as the BBC or the Guardian or the Economist or something like that, CNN. Really all sorts of nonsense. From all sides, right? So, previous president of the United States argued that climate change was a Chinese hoax. No. If it was a hoax, or if it is a hoax, then the Chinese had absolutely nothing to do with this, right? Particularly the Chinese in there is completely ungrounded. Also that it's a hoax is just complete nonsense. In the latest installment of Marvel, climate change is blamed on, global warming is blamed on the birth of a celestial. And the solution is seriously freezing the celestial, right? It's just like, where did they get this? Absolutely not true. So there is indeed, depending where you are, a small minority or a large minority, quite vocal, claiming it's all not true, right? There's also, on the other side, people who just talk complete nonsense from a green perspective, right? Politicians now go around claiming that climate change is a threat to civilization or a threat to the existence of humankind or even a threat to the planet. None of that is founded in any academic work whatsoever. We just won't go there. There is one academic paper in a very obscure journal that claims that because of climate change the Earth will explode. But in order to reach that conclusion, you need to make very strange assumptions about the composition of the Earth's core, assumptions that are directly contradicted by the data about the Earth's core. So no, the planet won't be in danger. Even if all humans go extinct, planet Earth will be fine without us, right? But also the prospect of a collapse of human civilization because of climate change is a very remote one. Talking about favorites, recently there was this interview with this woman who claimed to be a medical doctor, that because of climate change we will run out of oxygen. Completely and utterly unfounded. There is nothing in the academic literature that would suggest that climate change would affect oxygen levels. Of course, if we would run out of oxygen, that would be quite a severe problem, but no, that won't happen, right? So all sorts of nonsense you can get from either side, right? So what I'm going to do in the next half hour or so is essentially get us all on the same page. These are the facts, this is what we know, this is what we don't know. And that is then of course the basis for when we talk about the impacts of climate change, and earlier when we talk about how you would actually do climate policy, right? In order to do a policy, you need to understand where does the problem actually come from. So I'm going to start by talking about the greenhouse effect and the enhanced greenhouse effect. Then I'm going to talk about general circulation models briefly, and about some projections of climate change. So let's start with some observations. And there's 9 pictures here. On your left, we are looking at the 3 most important anthropogenic greenhouse gases. That's carbon dioxide, that's methane, and that's nitrous oxide or laughing gas, right? So this is the stuff that makes you giggle, right? You've probably seen, oh God, you've been in lockdown for 2 years, right? But before that, you've probably seen people go around with those balloons, right? That is this stuff. When you inhale it, it just makes you feel funny and makes your voice go strained. When it's in the atmosphere, it's a different story. There's the atmospheric concentration over the last 10,000 years. So that's roughly from the start of the agricultural revolution. And then in the smaller insets of the last 150, 170 years since the start of the industrial revolution. And if we look at CO2, what you see is that concentrations were roughly constant through most of this period. And then towards the end, they essentially go asymptotic, right? They start to skyrocket. Now that is a graphical illusion that has to do with the compression of the horizontal scale. If you look at the smaller inset, then you see well, it's not asymptotic, it's merely exponential, right? That concentrations go up. So concentrations don't go up, but they go up ever faster, right? That's what I mean by exponential. And it is actually roughly exponential. So that is what we know about these greenhouse gases. Stable for a long time, and then they go up roughly at the start of the industrial revolution, or from roughly the start of the industrial revolution onwards, I should say. We have another set of observations. This is the global mean surface air temperature over the last 150 years. I still think that the year is 2000, right? Over the last 170 years. Global average sea level and snow cover. And sea level has gone up, temperature has gone up, snow cover has gone down. Jurgen.
How do they know what the concentration was 10,000 years ago? How do they calculate?
That's a good question. Because 10,000 years ago we hardly had any chemists, right? And we definitely did not know about CO2 at that time, let alone that people could actually write and record this, right? So how do we know? So direct measurement of CO2 in the atmosphere started in 1958 by Charles Keeling. And that's essentially a chemical technique. You essentially trap some air and then you shine light through it and see what gets absorbed, and from that you derive what is the atmospheric concentration of a whole bunch of gases, right? Not just CO2. So that is the instrumental record, which, as I said, started in 1958. But this goes back to 8,000 years before the birth of Christ, or 10,000 years ago, right? So the way they did this is through the drilling of ice cores. So if snow falls on an ice sheet, snow is fluffy, so if snow falls, it traps air between the snowflakes, right? And if snow falls heavily, then the snowflakes at the bottom, then you essentially create little bubbles of ice, little bubbles of air beneath the ice, right? And if then enough snow falls, that actually gets then sealed, and the air that is in the ice is actually old air. Now if you go to Greenland or you go to Antarctica, you actually have a pretty sizable ice cap, and as you drill down in that ice, you meet older and older snow and older air. And that is essentially what they've done. They've drilled these ice cores and retrieved ancient air and then chemically analyzed it with modern methods. Right? So that is where this data comes from. And actually this record goes back, I think, 1 million years or so. And I only show the last 10,000 years here. But we can reconstruct CO2 concentrations as well as temperature. Way back when, temperature is reconstructed by the ratio of isotopes D13 and D12 of oxygen, right? But that's a completely different story. So that's where this stuff comes from. So these are the concentrations of greenhouse gases in the atmosphere. Here we have temperature goes up, sea level goes up, snow cover goes down. And these stories are completely consistent with each other. And in order to do so, we need to understand the greenhouse effect. So this is a graph of the greenhouse effect not drawn to scale. This is planet Earth. That is the sun. In reality, the sun is much bigger and much further away than suggested by this graph. Now, the sun is a big nuclear fusion reactor and sends radiation energy out into space in all directions, and a small fraction of that energy actually hits us on planet Earth. Now, solar radiation, as you may have noticed, the sun emits energy in the visible part of the spectrum, right? It's light that you can actually see the sun. That energy from the sun does a number of things. Some of it is reflected at the top of the atmosphere, some of it is reflected, actually all of it goes just through, almost all of it goes just through the atmosphere without any hindrance. Some of it is reflected at the surface of the planet, but a good bit of it is absorbed by the planet. And if you absorb energy, you store more energy and you warm up, right? More energy is warmer, that's the same thing. Now that cannot be the end of the story, right? If it were the case that the Earth just absorbed solar energy and absorbed solar energy and absorbed solar energy, then the planet would have evaporated a long, long time ago, right? So that cannot be the end of the story. But, of course, we also know that the Earth does not emit light. It gets dark at night. The ground does not light up. If it does, you smoked the wrong thing, right? Instead, the planet emits infrared radiation. So it emits energy, but in the infrared part of the spectrum. And it emits that into outer space. And on balance, the amount of energy that is absorbed is equal to the amount of energy that is emitted, right? It's just in a different part of the energy spectrum. Now that is where greenhouse gases come into play. Greenhouse gas is a gas, obviously, that is transparent to visible light, but opaque to infrared radiation. That's the definition of a greenhouse gas. So essentially what happens if you have a CO2 molecule that is floating somewhere in the atmosphere, if that CO2 molecule is hit by a ray of visible light, the ray just goes straight through it, as if the molecule wasn't there. If that same molecule is hit by a ray of infrared radiation, the molecule absorbs the radiation and gets into what chemists call an excited state. Now that cannot be the end of the story, right? Because if those molecules were there and just keep on absorbing energy, then eventually they would fall apart. That's not what happens. What happens is that the CO2 molecule gets from its excited state back to its base state, and in order to do so it has to emit energy again. Does that in the infrared part of the spectrum. The sky does not light up either. But the crucial thing here is that the emissions, the energy emissions from the CO2 or other greenhouse gas molecules is in any direction. Whereas the Earth's infrared goes to outer space, the infrared radiation that is emitted by CO2 molecules can be in any direction. It can be to outer space, it can also be back to Earth, can be sideways, can be any direction. That means that on balance it is easier for energy to enter the planetary system than to leave it. And the implication of that is that on balance more energy is stored on the planetary system than if there weren't greenhouse gases in the atmosphere. Right? So that is how the natural greenhouse effect works. Now, this is old science, right? Fourier in 1827 was the first to actually notice that the atmosphere warms the planet. Eunice Foote in 1858 was the first to pinpoint CO2. John Tyndall in 1861 was the first to actually work out the role of infrared radiation in this. And Svante Arrhenius in 1869 was the first to notice that, well, if we put more CO2 in the atmosphere, then the place would get warmer, right? So this is old science. If you don't believe what I just told you, and some people deny these basic facts, then you can do this experiment. You can do the experiment that Eunice Foote did in 1858. You can reconstruct it in your kitchen with a bottle, a plastic bottle, right? That's essentially how difficult it is, and there's plenty of instructions on YouTube to repeat this particular experiment if you don't want to take my word for it. So these observations are perfectly consistent. Based on first principles, if there's more greenhouse gases in the atmosphere, the place would be warmer. They've done some calculations and found that if the Earth had no atmosphere, then the planet would be 33 degrees colder than it is now on average. So the average temperature of the planet is around 15 degrees. It would have been minus 18 Celsius, of course, if there were no atmosphere, right? So this is important. And that is exactly what we observe. You've seen those pictures. These are essentially the same plus more. At the top we're looking at the land surface air temperature. Then the next one is sea surface temperature. That's the temperature of the water. This is the temperature of the air above the water, also going up. Sea level is going up. Seen those. Sea ice is going down, right? It's warmer, you would expect less ice. What you also see is, so these are the temperatures at the surface. That's the temperature there at the troposphere, so higher up in the atmosphere, also going up. This is not the temperature of the surface water, but down to 700 meters. It's going up. More ice is going down. This is Arctic sea ice. This is a glacier mass, snow cover. We've already looked at this. And an important thing that I haven't said, which is a particular complication in all of this. I talked about the three most important anthropogenic greenhouse gases, but they are going up. But the word anthropogenic there is important because there's also other greenhouse gases that are natural. And the most important one is water vapor. water vapor is a very potent greenhouse gas. And we also have Clausius Clapeyron, that is warmer air contains more water. So if the place gets warmer, the air can contain more water, and water is a greenhouse gas. So that strengthens the greenhouse effect. And indeed what we have observed is that the humidity is also going up. And this is an important positive feedback. You put more CO2 in the atmosphere, the place gets warmer. If the place gets warmer, there's more water vapor in the atmosphere, more water, and if there's more water in the atmosphere, it gets warmer again, right? And that's an important feedback that has now also been observed, and has now also been confirmed with observations. Now, this is just first principles, right? The physics of all this is quite complicated. So what people have done is build so-called general circulation models, which are essentially big, complicated computer models that have all these processes in there. The CO2 in there, and what does it do to the energy balance and the other greenhouse gases, and then the water feedback, and so on and so forth. And that is essentially what people have been building. And these general circulation models are the second most complex models, second most complicated mathematical constructs built by humans. The most complicated ones are the protein folding models, but general circulation models come second. And essentially what these models do is, they're essentially the same models as are used for weather forecasting. So they just represent the physics of the system. And they are quite complicated. And the reason is that the climate problem is quite complicated. I talked about one complication already, that's the water vapor feedback. I'm going to talk about a couple of more complications before I show you some validation of these models. And then we're going to take a break, and then we're going to talk about scenarios. So what you're looking at here is the change in the change in the energy balance, known as radiative forcing, relative to 1750. So this is essentially how much more energy is in the planetary system relative to the year 1750. And the unit here is in watts per square meter. Watt is an energy unit, square meter is an area unit. So essentially you can think about this as how much energy falls on a small piece of land. At the top you're looking at CO2, and what you see is that yes, that has a big change in the energy balance. Then we're looking at some of the other greenhouse gases. CH4, methane is there, laughing gas is there. And the first complication that you see here are the so-called halocarbons. Halocarbons are CFCs and HFCs, things you have in your fridge and in your air conditioner, but also used for the manufacture of chips, computer chips, and so on and so forth. These gases themselves are greenhouse gases, so they warm the planet. But CFCs destroy ozone. This is the cause of the hole in the ozone layer. But ozone is also a greenhouse gas. And that is why we have a negative effect, a cooling effect. This is actually smaller than the warming effect from the CFCs themselves. We have a whole bunch of air pollutants, that in the air transform themselves into greenhouse gases. That's carbon monoxide, those are the volatile organic compounds. They have a warming effect. But we also have nitrogen oxides, NOx, not to be confused with N2O, right? This is nitrous oxide, these are nitrogen oxides. They destroy a lot of ozone and have a cooling effect, right? We also put all sorts of dust into the atmosphere, all sorts of particles we put into the atmosphere. Mineral dust, sulfates, nitrates, black carbon, organic carbon, all that stuff we spew out from factories and cars. And those have different effects. Some of these particles actually absorb infrared radiation and therefore lead to cooling. Others of these particles actually reflect sunlight. They actually make sunlight scatter back into outer space. And they have a cooling effect, therefore. But you see that the chemistry is complicated, physics is complicated, and actually we're not quite sure whether these things had a negative effect or a cooling, a negative effect, a cooling effect, or a positive effect, a warming effect. Now these particles also serve as nuclei for cloud formation. And that is the bar that you see here. This is another thing that complicates the whole story. And clouds are complicated in and of themselves, right? We're in winter now. If we have a clear night, no clouds, it gets very cold, right? In summer at daytime, when it's a clear sky, it gets very hot, right? So the effect of clouds depends on whether it's winter or summer, day or night. It also depends on whether it's low clouds or high clouds, whether they keep the warmth of the earth in or whether they keep the heat of the sun out. So clouds are quite complicated. And of course, clouds are part of the climate system, right? If it gets warmer, if winds change, if there's more water in the atmosphere, clouds change as well, right? So clouds are complicated, but clouds also have a direct effect on the temperature, right? So this is another important feedback that these general circulation models have to deal with. People think that on average this was a negative effect, it cooled the place down, but they're quite uncertain about this. Other things are going on. There's albedo changes. Albedo is essentially a measure of how much energy does the Earth's surface reflect back into the atmosphere, into outer space. And there's all sorts of things going on with the albedo. As you may recall from last summer, if you wear dark clothes, you actually get very hot. But if you wear light clothes, it's actually much cooler in summer, right? Now the same is true for planet Earth. So if you have ice, it's light, and it actually reflects a lot of sunlight, right? So that cools the place down. But then if the ice melts and is replaced by darker water, it actually heats the place up. So the melting of the ice over the North Pole actually is another positive feedback effect. The more ice melts, the warmer it gets, and the same is true for the snow cover. But also, if you, in a distant past, you may recall flying and looking out of the window of the aeroplane and sort of looking at the landscape below. Forests are dark, trees are dark green, grass is light green. So if you cut down the forest and replace it with grassland, you actually have a lighter surface, and that then cools the place down, right? Rather than warms it up. And all these things go under the term of albedo change. And then of course the sun itself is the source of all our energy, and the sun is not constant either, but what you see is that yes, the sun has warmed, or an increase in solar radiance has warmed the planet, but only by a tiny little amount, right? So that's the first complication, or the seconds. There's all these things that are changing, right? It's not just greenhouse gases that we're putting out. There's all sorts of other things going on with the climate system as well. And then the climate system itself is not simple either. I'm going to do one more slide and then we're going to break for 10 minutes or so. Now the final thing that you need to worry about is what is going on with the gas cycles. In this case, the carbon cycle. It's a complicated graph. So let me tell you what it does. The rectangles, let's call them that, are stocks. This is the amount of CO2 that is in the atmosphere, and the amount of CO2 measured in billion grams of carbon was 589 in pre-industrial times, say in 1750, and so that's a black number, and then since then we have added 240 to that, right? So that is what those numbers mean, and of course there's a little bit of uncertainty about this. So that is what the boxes mean, right? So there's 590 plus 240 petagrams of carbon in the atmosphere. There's a whole bunch of carbon in the ocean sediments. There's stuff that is dissolved in the water, the surface ocean or deeper ocean, and you actually see that's quite a bit, right? That's 37,000 compared to the 600 that you see there, right? So these are all stocks of CO2. The arrows are the annual fluxes. So what you see is that through photosynthesis, I don't know why they changed notation here. Through photosynthesis in pre-industrial times, 110 petagrams of carbon were sucked up by plants. So plants sort of take CO2 from the air, they take water from the soil, and then in photosynthesis combine the two into two products. One is oxygen that they don't like, and they put it out in the atmosphere. We do like oxygen. And then they take the C from the CO2 and the H from the H2O from the water, combine it into a carbohydrate that we then recognize as a leaf or a root or a stem or something, right? That is what plants do. So they take up quite a lot of CO2 from the atmosphere, 110 petagrams per year in pre-industrial times. But then also, when they die down in fall, a lot of that gets sent back into the atmosphere, right, as plant material rots. And there's very substantial fluxes going on there. And similar things, but more chemical than biological, are going on in the ocean. The ocean absorbs CO2 and emits CO2, and those fluxes in pre-industrial time, were around 60. So that is what the arrows mean. Now, the reason that we worry about climate change is that there's also a whole bunch of CO2 stored in what we call fossil fuels, but which are essentially ancient plant material, right? So I talked about plants taking up CO2 and then dying back and rotting, but some of the plant material is not rotted, actually is stored underground and then compressed over millions of years and transformed into coal or oil or gas. Now, for a long time, that was just safely stored somewhere deep, or not so deep, in the crust of the planet. But what we have been doing since the start of the Industrial Revolution is digging it up and burning it, and that emits CO2. And since the start of the Industrial Revolution, we've taken around 365 out of our fossil fuel reserves, and as you can see in these numbers, there's a whole lot more there, right? So we can continue this process for a long time. And some 5 years ago, 10 years ago, the annual flux of fossil fuels was around 8 petagrams of carbon per year. And you may think, well, this is simple, this is trivial, right? Humans emit 8, but plants emit 120, the oceans emit 80. So what are we talking about, right? 8 versus 200, that's small fry. The problem with this red arrow is that there's no counterbalancing force. It's true that the ocean emits a lot of CO2, but the ocean also takes up a lot of CO2. And it's true that the terrestrial vegetation emits a lot of CO2, but it also takes up a lot of CO2. Humans just emit CO2, but don't take it up again. Actually, we are lucky, fortunate, that of the 8 or so petagrams of CO2 that we emit every year, roughly half is taken up by mostly vegetation and somewhat less the oceans. But half of the CO2 that we emit does not end up in the atmosphere. It ends up in the ocean where it's innocent roughly, or ends up in bigger plants and trees. And about half accumulates slowly in the atmosphere. So that is the carbon cycle. Now the problem is that all of these things depend again on climate, right? So CO2 emissions, we burn fossil fuels to keep ourselves warm, so that depends on climate, or for air conditioning to keep ourselves cool, so that depends on climate. This is essentially plant growth, so that depends on climate, right? The processes here are also dependent on climate. So there's another feedback going on here that if you change the climate, you also change the carbon cycle, and the carbon cycle is what drives the climate problem in the first place. So we have a horrendously complicated system. What I said before the break is two things. The climate system is very, very complex, right, with many, many moving parts, moving in all sorts of different directions. And I said, well, they've built very complicated computer models of this system. And the question, of course, then comes to your mind is, how good are these models? Do they actually have some sort of predictive skill? And this graph tries to convince you that it does. This is taken from the 5th assessment report of the Intergovernmental Panel on Climate Change, which is a UN organization that every 7 years or so publishes a big review of climate science as well as climate policy and impacts of climate change. And over the years they make more and more and more and more complicated graphs. So let me take you through what it shows here. So at the bottom we're looking at the global mean surface air temperature. We've seen this one before, but now it's smoother. That's the black line that we're looking at. And then this is the temperature evolution over land, ocean heat content. And then here we're looking at all the we're looking at all the continents as well as all the oceans and the temperature evolution over that. And those are the black lines that you're looking at. Now in pink, we're looking at model results, where they've taken these climate models, started them in the year 1900 or 1910, and ran the 20th century. And in pink, they included in those models everything that we suspect might change the climate. So greenhouse gas emissions and the aerosols I talked about, and the sun and volcanoes going off and all that stuff is all in there. And then the result is the pink range, and this pink range is everywhere. The reason that there is a range is that by now there are about 35 of these climate models, mostly in Europe and North America and Japan, but also a few outside there. A few in China, but mostly this is a rich man's thing, and a few women as well. Not too many. So that is the pink range that you see. So if we include everything that we think might change the climate, including greenhouse gases, then what we see is that the observed warming over the previous century is bang in the middle of the projected warming. So nothing strange happening there, right? This is what theory we observed, what theory predicted would happen. And not just true for the global average, but actually if you go for this graph, for the continents and for the oceans as well. Now there's a second set of model results here, and that is the blue range, and that is if all the natural forcings are in there, so the sun changing and volcanoes, ocean dynamics, what have you, but not the aerosols and not the greenhouse gases. And then you have a range that actually does not show warming. And I mean, this is a range of model results, it's not a probabilistic confidence interval or anything like that. But what you see is that without CO2 emissions, without greenhouse gases, the observed warming is actually very hard to explain, would be very unusual. Whereas with greenhouse gases, it is bang in the middle of what you would expect. Which suggests that yes, the observed warming of the planet is because of our emissions of greenhouse gases and other substances that change the climate, right? So this gives you some confidence that A, warming is indeed due to humans, and B, that these models that they're using are skillful. They can actually forecast things that we have observed, right? Some confidence in these models is appropriate. So having established that, we can then project into the future. So this is the observed warming again, and these are projected futures. There's two things going on in the future. One, we have different colors, which are different ways in which the future may unfold, the number of people that there are, the amount of energy they use, what energy they use, and therefore how much CO2 they emit, right? So those are alternative emissions futures, essentially. And then the range around the central line is again a range of model results. And you see that the future is fairly uncertain. By the end of this century, the year 2100, that's roughly by the end of your lifetime, right? We could sort of like see a warming of 1 degree, but maybe 6 degrees, right? For the world average. And if you then move into your children's and grandchildren and great-grandchildren, warming can be from 1 degree up to more than 12 degrees, right? So that is the sort of future that we can expect if emissions indeed go this way, right? And we'll talk about it extensively next week and the week after, what emissions are actually can be expected to do in the future. Now, this is for the global average temperature, which is perhaps not the most interesting or the most relevant. Here we're looking at a spatial pattern of temperature change for 4 alternative futures of emissions. Low emissions in the future, high emissions in the future, two intermediate cases. For 3 time periods, this is the middle of the century, 2050 or so. This is the end of the century, 2090. And this is the end of the next century, 2190, right? So that is what you're looking at. And you see a couple of obvious things, right? That the darker the color, the warmer it gets, right? The further you will go out in the future, the more warming you see. Talked about that. Obviously, if emissions are higher, you would see more warming as well. But there's 2 additional patterns that you see. One is that warming is more pronounced over land than over water. This is again basic physics. Water has a greater heat capacity than land. That is, land warms up faster. And that is of course the reason why in winter it gets dark first before it gets cold, and then in spring it gets light before it gets warm, right? That has to do with the heat capacity of water slowing, that the meteorological seasons lag behind the astronomical seasons. So that is one thing that matters. And it matters because most humans live on land, right? Very few humans live on the open ocean. And therefore this global warming of 1 to 6 degrees is for the world as a whole, including the 70% that is ocean, right? Over land where we live, it is actually, warming is actually more pronounced than those numbers. So that is an important thing. A second pattern that you may notice is that warming is more pronounced towards the poles than towards the equator. So the north, the high north and the high south warm faster than the tropics, which you may sort of take as a sort of a relief, right? Because essentially temperature gets more equalized. There's 2 other patterns that are not shown here. One is that warming is faster at night than at day, and second, warming is faster in winter than in summer. Again, some equalization going on there. So those are the temperature patterns. Of course, it doesn't change there, right? If the place gets warmer, then more water evaporates, the air can contain more water, and therefore you would also expect changes in rainfall. And secondly, what you see is that warming is not uniform over space, and that means that pressure patterns will also not be the same in the future as they are now, and that means that wind patterns will change as well, and as a result also clouds will change. So you would also expect changes in rainfall. And that is shown on these maps. This is for one scenario only, a very high emissions scenario, again 4 time slices. The near future, the more end of the century, end of next century. And now we're looking at winter, spring, summer, fall in the northern hemisphere, right? So those are the patterns that we're looking at. And what you see here is, and then in blue we're looking at wettening, more water falling. In brown we're looking at drying, less water falling. And what you see is a much richer spatial pattern, right? Some things are recognizable, some things are not so recognizable. One of the things that you may see is a general tendency for rains to be pushed further towards the pole, away from the equator. Now that is not so much an issue in the northern hemisphere, because to the north of us there's land. but it is an issue in the southern hemisphere, particularly over southern Africa. What you see is that the rains that used to fall over southern Africa in the future will fall over the Southern Ocean. Which is no good to the fish there, right? They don't care if it rains or not. But it is fairly bad for the farmers that are here, right? It's not that the rain will disappear, it's just that the rain will fall over sea. It's pointless from an agricultural perspective. So that is one pattern that you may notice. Another pattern that you may notice is if you look at where we are, if you look at the winter, Great Britain is actually fairly dark blue, but if you look at summer, Britain turns brown. Now, you may have heard people say that climate change will bring more floods and more droughts. And you may have heard some skeptics saying, well, these guys are nuts, right? How can it be drier and wetter? How can you have more droughts and more floods? What sort of inconsistent story is that? Actually, it's more floods in winter and more droughts in summer is the prediction. Of course not more droughts and floods at the same time in the same place. That wouldn't make any sense. So in this part of the world, actually over most of northwestern Europe, you can expect more rain in winter and less rain in summer, which is a particular issue for the south of England because we have a flood problem in winter already that is going to get worse, and we have a drought problem in summer that is also going to get worse, right? So the forecast or the projection with climate change is exactly the opposite of what we would like to see. We would actually like less rain in winter and more rain in summer if we could have our way. So that is an important thing to keep in mind here as well. The third thing, and we'll come back to that in, I think, week 6, but it may be week 7, is the dots and the dashes that you're looking at here. So if we go back to the temperature map, we see dots everywhere. You may have wondered why did they put them in there. It just makes things ugly. Dotted areas are those where all or most models agree on the sign of change. And dashed areas are where some models say it's going to go up, and other models say it's going to go down. And there's no agreement on the sign of the change. And if you look at where are the dashed areas, there's just huge areas of the planet where we don't know whether it's going to rain more or less in the future. That includes large parts of Africa, right? We just don't know. Large parts of Asia, the Indian subcontinent. We don't know whether it's going to rain more or less in the future. We do know that the rainfall patterns will not be what they are now, because that would be physically impossible. If climate changes, then rainfall must change as well. But because of the complications in the climate system, we actually don't know whether it's going to get wetter or drier in these places. Which of course is an enormous problem if you're trying to prepare for climate change, because you don't know what you are preparing for. Right? With temperature it's easy, it's going to get hotter in summer, so we all need to get air conditioning. You know how to respond, but if you don't know whether it's getting hotter or wetter or drier, you actually are in trouble if you want to prepare, right? There's other implications of climate change. The one that often pops up is sea level rise. Here are again some projections. By the end of your lifetime, sea levels could be 30 centimeters higher than they are now, up to a meter higher than they are now. Most people, when they think about sea level rise, they think about ice melt. that is actually not the most important process. The most important process here is the expansion of water. And you may think that is strange, right? If you get a cup of tea or a cup of coffee and you let it cool down, it doesn't shrink, right? It's not that if you let your tea cool down, all of a sudden it's smaller. Well, it is actually, just not visibly. So how can it be that if the ocean warms, yes, physics will tell you that then seawater expands, how can that lead to sea level rise? Well, the reason for that is, yes, water expands as it gets warmer, but only by a tiny little bit. The problem with the ocean is that it's on average 3 kilometers deep. So if a column of 3 kilometers expands by a little bit, and you are a tiny human, you're 1.5, 2 meters tall, then that tiny little bit on that 3 kilometers is actually large relative to you, right? So that is why expansion actually matters, thermal expansion actually matters. That's because we are so small relative to the ocean. Again, this is not a uniform pattern. Here you're looking at the projected sea level rise spatially over all the oceans. This has to do with changes in pressure patterns, changes in warming, as well as changes in gravity. Particularly the East Antarctic ice sheet is so large and so heavy that it pulls water towards the South Pole. And that is a large effect. If there were no ice cap over Antarctica, then sea levels in Europe would be 13 meters higher than they are today. So that's an issue there, and that partly explains why this pattern is there. And of course, there's also ice melt, right? Obviously, when ice melts and that water runs into the ocean, then sea level goes up. What is not important is that the ice that is floating on the water on the North Pole, if that ice melts, then sea level does not go up, right? Because at the moment the ice displaces the water, and if it turns into water, then nothing has changed. That's Archimate, right? But if Greenland melts, the Greenland ice cap rests on land. If that melts and it melts completely, then you're talking about 7 meters sea level rise or so. The West Antarctic ice sheet also rests on land. The problem with Greenland melting is that we don't know how fast this would happen. Greenland is actually pretty warm. I mean, a few degrees would sort of like tip Greenland into permanent melting, but we don't know how long that will take. Projections for this vary between a few hundred to a few thousand years before Greenland is has completely melted. The same would be true for the West Antarctic ice sheet. But the problem there is that it's a glacier and the whole thing may slide into sea. And even if the West Antarctic ice sheet does not melt, and is not likely to melt for a few thousand years, if the whole thing slides into sea, then also that would cause sea level rise in the order of 5 or 6 meters. If East Antarctica were to melt, then we're talking about 60, 70 meters. 60 or 70 meters of sea level rise, right? So there's a lot of water there, but all of these things are sort of like, yeah, maybe by the end of this millennium, these things may happen. Definitely not. Definitely is a hard word. Very unlikely to happen during your lifetime, right? And then other things will change as well. And this is the final slide. We're not going to make a head start on next week. I talked about rain, I talked about temperature, I talked about pressure patterns and therefore wind direction. There's of course also storms that would likely change. People often worry about tropical storms hitting Europe, hurricanes, typhoons, those sort of things. That is not likely. The physics is such that, yeah, you need to be in the tropics to have a tropical storm, and it's not that the subtropics will turn into tropics. So we will probably not see a change in the area of tropical storms. We will probably also not see a change in the frequency of tropical storms. It may even be that they will become less frequent rather than more frequent because of climate change. But because these things are essentially driven by temperature gradients and essentially driven by the amount of energy that is in the system, it is likely that tropical storms will become more violent. That is, wind speeds will go up. And the same is true for the sort of storms that would hit England, or that hit England. Don't expect them to be more frequent, but we do expect them for them to be more violent. Now that is a problem from an impact side, because more frequent storms is actually not a big deal, right? If a storm that came once in every 10 years now comes once every 8 years or once every 5 years, if it's once every 5 years, then essentially you double the damage, right? So that is not such a big deal. But intensity is a big deal, because the force that the wind exerts on your house or on the tree that is standing next to your house is the wind speed to the power 3. So a relatively small increase in wind speed means a large increase in the force exerted on your property, and therefore a large increase in the damage done. So it's the intensity that is going up, and it's the intensity that we should worry about rather than the frequency. Similar things for rainfall. I talked about rainfall patterns. The thing that is not listed here is that the whole system is more energetic. The atmosphere is warmer and therefore contains more water. And if there's more water in the atmosphere, that means it can rain harder. And what you can expect is an intensification of the hydrological cycle that is probably longer, longer droughts interspersed with very heavy rainfall, short bursts of very heavy rain, which of course then cause all sorts of problems with floods and what have you. Now the final thing I'm going to say for today is about ocean acidification. So I showed you this cartoon where I said there's a whole lot of CO2 in the ocean, right? And the reason that there is CO2 dissolved there has to do with the laws of partial pressure. If there's CO2 in the atmosphere, then there's also CO2 in every body of water that is in direct contact with that atmosphere. And that CO2 is then dissolved in the water, not just in the ocean, but also in all surface waters. Now, everybody calls CO2 CO2 or carbon dioxide, but that is the chemical term, that's the technical term. The English word for CO2 is carbonic acid. And the key word here is acid. So CO2 dissolved in water is an acidifying substance. So if there's more CO2 in the atmosphere, there will be more CO2 in the ocean. If there's more CO2 in the ocean, that means that the ocean is more acidic, less alkaline. Now that's not so much a problem for you, because it's not that seawater will get very acidic, so you can go swimming in the sea without a problem, and that is because we and a great many other animals have our skeletons on the insides of our bodies. Our skeletons are, of course, made of calcium. And calcium and acid is a very bad combination for the calcium. But you can just go swimming in the sea. It won't dissolve your skin. It won't get into touch with your skeleton. If you're a lobster or a mollusk or something like that, then you have an exoskeleton. The calcium is on the outside of your body. And that means that if the water gets more acidic, your skeleton will gradually dissolve, and you will have greater difficulty if you're a young one to grow a skeleton. Now, this is not just mollusks and lobsters and those sort of things. Also, a lot of plankton has exoskeletons, and of course, coral reefs are built of calcium, right? So if there's more CO2 in the atmosphere, ocean water will become more acidic, and everything that is made of calcium that is in direct contact with the water, including the White Cliffs of Dover, by the way, will be in trouble, right? And we can expect things there, and you may say, oh, that happens to other species, right? But of course, these species are at the bottom of the food web, and we eat things that eat things that eat things that eat things that actually depend on those exoskeletons. So that is, ocean acidification is not something that should be forgotten, and is a key part of climate change and has the exact same causes. So that's all for today.